All right, we're going to do our 2 discussion summaries now. So I think the first one was solar neighborhoods. So Bob's going to tell us if you guys decided whether there was anything special about the solar neighborhood.
Okay, well, we started off with the just doing introductions. We had a fairly small group and saying, do people think that we live in a special environment? And no one really did. And then we discussed it. I think the conclusion is we live in a special environment only in the sense that like every child is special to their parent, or every moment of your life is special. I mean, you can find a set of circumstances and things that are unique in that moment in time. But when sort of viewed with a broad brush, we couldn't find the most special thing we could find in our solar environment was the Radcliffe wave, which is not a freak thing, but it seems to be maybe 100, at least if Sarah's simulations were any judge, 100 of those in the galaxy. So it's special to be near one, and it gives us an opportunity to study something that's a little special. In terms of where we are in the galaxy, of course, we're special to be 8 kiloparsecs out, but that's not special because you got to be somewhere. And as we go around in our orbit, we maybe traverse spiral arms, but most of the time would not be spent in a spiral arm. And we are not in a major spiral arm. We have this thing called the Radcliffe wave near us, but that makes us sort of not special. So the final thing was, we live in a local bubble, not special. One thing that came out in the discussion is we're learning more about the bubbles around us, whose properties are pretty like the local bubble. So even the local bubble is not a special bubble. So then we were really reaching, is there anything special that we can find about our solar neighborhood? We talked about the surface density of gas and stars, the surface density of star formation. When you look at those numbers for our radius and the ratios, nothing is special about those numbers. So the good news is we are spectacularly average, which is just like the specialist thing you could be. Yes?
What about surface density of Voyager spacecraft?
Well, we don't know that, do we? So one little thing I learned is that in terms of the solar motion through this, we are a little special in the sense that our sun cruises through this environment at a faster rate than a typical star. So we're a little special in the sense that we get to change our view more often than a typical star. So I guess that's it. So.
We are not special. And now Joel and Emma are going to give a joint summary of how molecular clouds turn into protoclusters.
Cool. Okay, I'll just start. So I think unlike the last group, which seems to totally agree on things, we had the opposite problem. So this is just a massive set of disagreements that I'm going to describe to you. So they even disagreed with the premise of the question. So the question was, what are the lifetimes of molecular clouds to protoclusters? And the basically, in order to define that, we had to try to define what the beginning and end point of a cloud is. And jumping ahead to the end really quick, we couldn't even agree that there is a single lifetime for a cloud because they could be cyclical, meaning there is no beginning or end, and the whole question is moot. So, and we also found the observers and the simulators couldn't agree on their definitions of beginnings or ends. So we have anyway. That's the overall summary: is that there was a heck of a difficult time knocking this down. Okay, so now the details. Would you like to start with a couple of specifics?
I'm up here because I was the scribe. And
I needed help.
So we basically started with like asking what is the beginning point. We kind of first split into the simulators and observers to see like if we had an agreement. Thought we had an agreement on when it becomes filamentary, but then we threw that out at some point. And I think we did kind of reach the point where like there is kind of multiple generations of what is the beginning of a cloud if there's going to be a cyclical kind of nature. Then we moved on to asking like what is the end point. Someone made a really good point about instead of trying to go from beginning to end in terms of defining a lifetime, maybe going from end to beginning, like a backward timeline might make more sense or might help answer that question better. Don't know if we really, one of them was, is a protocluster even the actual end of a cloud? Like, where do you define that? That kind of goes back to the question. But then I think we made a really good kind of segue into like, why do we care about what the lifetime of a cloud is? Like, what does that tell us? We were talking about how timescales tell you about energy budgets, and that's something that's really important. And also like star formation efficiency, what percentage of gas is turning into stars. These are some of the information we're trying to get from answering this question. And then what are the observables? Like how can we actually compute these defining numbers? One thing I forgot to mention is there was some talk about like if the beginning of a cloud is defined by some kind of density threshold, how would we come up with that number? I don't know if we actually stuck with that.
Well, to jump in on the part of it, the issue was that density threshold by itself was not a sufficient parameter. You had to obviously throw in other factors, turbulence, radiation fields, things like that. So even if you had a number, it couldn't be a number. It would have to be a cluster of numbers that you could, just to start with a definition of threshold point. But
yeah. So then, yeah, we went back to observables. Someone mentioned depletion time, I guess like current rate of star formation over the current number of stars, maybe something like that. Talking about the 3.3 micron PAH feature is a good, observable for like where are the clouds, I guess.
I think the depletion time might have been the rate at which the gas is being converted into stars divided by the amount of gas, but the concept's the same.
Yeah, and then we really tried to come up with a summary thought because no one in the room, we couldn't really get the whole room to agree. That was a lot more difficult. I think we kind of ended on like, are discrete clouds even really a thing? Because of this kind of constantly evolving question about it. And is a beginning and end point even, does it mean anything? My last point is defining something that's not necessarily correct but universally applied valuable? I don't know.
Maybe a lie, but maybe a useful lie.
Yeah.
Would anyone else like to throw anything in from that discussion? Because I don't know if we covered all of it, but there was a lot. All right. Thank you.
All right. Thanks everybody for 3 days of great discussion sessions.
Right time?
Posters.
What are you doing, Chris?
Your poster flash talks.
Poster flash talk people, come up here.
You know what you're doing.
Know what I'm doing.
Scientists in the room.
We're gonna start off with Mordecai.
Oops. Mordecai the Fourth here. So the torch star cluster formation simulation package is actually quite general purpose. It uses a mused coupled flash and n-body codes, and we've done a bunch of work with it. Some samples are here. We find subcluster formation, non-uniform subcluster formation, non-uniform gas expulsion. It doesn't just go out in a spherical shell. When subclusters fall in, they can generate sprays of runaway stars. These are observed. Our spherical clouds without jet feedback show very high star formation efficiency at 1 million solar masses, not quite so high at 10 to the 4 solar masses. But these are probably worst case scenarios because of spherical clouds. But we have added jets and we're starting to run with them, and they lower the star formation efficiency locally during the early times of clusters. And now we want to see what it does to one of these 10 to the 6 solar mass monsters. And we're starting to add yields. And we're starting to add yields and looking at how secondary subsequent star formation can get variation from things like massive binaries, and I'm probably out of time.
Yep. Now we're gonna go with Tobin.
Hey everybody, I'm Tobin. I'm a grad student at the University of Washington. I do all kinds of star cluster stuff, but today I'm going to be talking about some work I did at the CCA with Mike Grudich and Julian Delcanton on the StarForge simulation, so talking about AU level resolution, specifically on the time scales of embedded star formation. So hopefully everybody that was at that discussion section will come to my poster and chat. So specifically up in the upper left, we have this some snapshots from the Starforge simulation, and then thinking about the timescales on which the stars in that simulation become unembedded. So we've thought about the association as a whole down here. Beth, please don't get mad at me for using freefall time, but we kind of classify the cloud in terms of its freefall time as well as in million years, and see a very quick gas expulsion phase, and we see that this expulsion is driven by the individual stars in the simulation. So on the right, we have a GIF of the individual stars in that simulation, and they follow the same extinction tracks no matter when in the formation process they form. So if you want to see stills of these this GIF, please come to my poster. It's the horizontal one because it was used for another conference. But thanks.
All right, Aisha. Aisha. Yes.
Hi, I'm Ashish Gupta. I'm a postdoc at the University of Virginia, and I'm going to talk about interactions between young stars and molecular clouds. Interestingly, the textbook description of star formation suggests that protostars don't interact with the molecular clouds. If you know about the class 0, class 1, class 2, class 3, there's no environment in those pictures, but we are realizing they do interact, and this is not true. I don't know why I said don't. Anyway, so we want to study these interactions, and the first step, so far we have some serendipitous detections of these interactions in terms of these elongated structures seen by ALMA called streamers, which are probably trails of infalling gas. And in my PhD, I studied like ALMA observations are expensive, pan-stars, DSS are cheap. Can we use reflection nebulae to get the statistics? And it seems like this phenomena should be common. Then how to characterize them, how to make sure that this is indeed in falling motion, and what are the dynamical properties, how much it can impact. I developed this code called TIPSY, which fits in falling trajectories to these morphology and velocity gradients of these structures. And I'm happy to talk about applying TIPSY in different kinds of infalling and rotating systems. And this has been used in many streamers now. And finally, to actually have a systematic survey, we really need an ALMA large program. We don't have a large program dedicated in studying environment, but the next best thing is DECO, which is an ALMA large program studying 80 disks in 4 star forming regions. And we find around half of these sources have something large scale around them. So protostars, planet formation, this is not happening in isolation. And yeah, please give us 3D maps of these regions. Thank you.
All right, a minute.
Right. Hello, I'm Jimena Rodriguez. I'm postdoc here at FCCI. And in this work, we use the 3.3 micron pH emission to detect very young star clusters, which are still surrounded by the dust and gas. We did this in the first 19 galaxies observed with fast JWST. And one of our main conclusions was that the embedded phase of star formation is very short, less than 3 million years. And this is important because it's before supernova happens. So the pre-supernova feedback had to be important. In a new project, we also are looking for massive young stellar objects in M33 and a couple of more nearby galaxies. So go to check my paper, it's right next to the door. Happy to talk more about this. Thank you.
And lastly, we have Ashley.
Hi, everyone. My name is Ashley Lieber. I'm a third-year grad student at the University of Kansas, and I'll be continuing on from Becca's talk earlier about NGC 253. This is the nearest nuclear starburst galaxy to us. And it hosts a group of about 14 superstar clusters in its very central region. So the work that I'm doing is using ALMA data of some higher excitation molecular line tracers that are showing asymmetries. That's showing indications of feedback in these really early pre-supernova stage of feedback. So we're trying to leverage those observations and build an evolutionary framework to understand how it goes from infalling gas to its early dispersal phases. So if you have any questions or would like to talk more about this, please stop by my e-poster. Thank you.
Anything from the chairs? That's a break. We'll be back in 30 minutes. Oh, yeah? All right, we're back at 4.
Thank you.